Hi, I will be talking about the paper Hawk's process with flexible triggering kernels. Attention-based models capture the historical representation by using a latent vector and a similarity function such as exponential dot product. The latent vector for each event is built from its type and temporal embeddings. Temporal embeddings inject sequence order information, and type embeddings provide learned vector encodings of event types. Our model uses the triggering function of the Hawk's process to replace the similarity function used in attention-based models. Here, Q indicates the triggering kernel between two event types. We chose a rational quadratic function to estimate the decaying effect of the triggering kernel, which can be thought as a more flexible generalization of the squared exponential. In addition to the rational quadratic function, we also introduce a gating mechanism to capture the localized behaviors that cannot be captured by simple decaying kernels. This figure highlights the difference between a regular decay versus a localized behavior. By multiplying a sigmoid gate with a rational quadratic kernel, we can capture both the decaying and localized effects. We want to estimate a kernel for each pair of event type, and this means the total number of parameters scale quadratically with the number of available event types. Rather than estimating a kernel for each pair, we use feed-forward networks whose inputs are the concatenation of pairwise type embeddings. This allows us to scale the total number of parameters linearly. Now let's talk about experiments and the results. First, we will look at how our approach performs when it comes to learning the underlying pairwise kernels of a two-dimensional Hawk's process. Each of these figures shows a triggering kernel for an event pair and its estimation. We observe that the sigmoid-gated kernel outperforms all the baseline models when it comes to capturing both the decay and the localized effect. Second, we will look at the prediction results for the last events. For the arrival time predictions, we report the root mean squared error. Our model, SGHP, outperforms almost all the existing approaches in terms of arrival time predictions. For the event type predictions, we report the F1 scores. In cases where the SGHP fails to outperform all other models, we attribute this to the class imbalances. Finally, let's explore the interpretability of our approach. We trained the model on COVID-19 patients admitted to an emergency department, treating each patient as a sequence and their movement across different rooms as events. The figure on the left allows us to compare the likelihood of a patient transitioning from the emergency department to the ICU versus the step-down unit. The figure to the right highlights the higher likelihood of a patient dying within an ICU unit compared to the other hospital rooms. Thank you for listening.